where most of the data is located, so on. That's connected with the group frequency table. The stem and leaf diagram is an alternative to the histogram. The advantage of the stem and leaf diagram is that retains all the original observations. The final method for displaying data is the box whisker plot. It again shows you where the data is located, how spread out it is. The advantage of the box whisker plot is it's very compact. So several populations can be illustrated very easily on the same graph. An example, here's the baby boom. This is data that gives you the age distribution for Canada from 1921 to 2006. I'll use a histogram to show you how the age is distributed for different time periods. There's 1991. The hump here at the beginning is probably post First War baby boom. This is 1931, 1941, and then after the Second World War, there was also a baby boom. See it there with higher frequencies for the younger age groups. 1956, and basically the baby boom, as time goes on, the baby boom moves through the population as they get older, as the baby boomers get older. There is some summary statistics. Median age for males, median age for females from 1921 to 2006. There's a graph, the median age. Again, you see after 1940. And this is the baby boomers moving through time from 1960 up to 2000. There's the population of Canada from 1921 to 2006. There's a graph of that. Some summary numerical measures of central location, the mean and the median. The mean measures the center of gravity of the data. The median is the point that splits the data into two equal parts. Percentile, these are measures of non-central location. There are points underneath the distribution that have a certain percent below. Quartiles are certain percentiles. The 25th percentile, the median is the 50th percentile, the upper quartile, Q3, is the 75th percentile. Measures of variability, measuring spread. One of the easiest calculations is the range. It's the maximum minus the minimum. So it's the length of the interval that contains 100% of the observations. The interquartile range is the third quartile minus the first quartile. This will be the length of an interval containing the middle 50% of the observations. Here's an example with verbal IQ. The median, the midpoint, is 96. They're arranged in increasing order. Q1 is the median of the lower half, 89. Q3 is the median of the upper half, 105. You also have the largest and the smallest. The difference between the largest and the smallest is the range. The difference between Q3 and Q1 is the interquartile range. The sample variance, this is another measure of variability. Recall that the mean is the sum of the x values divided by n. It's the center of gravity of the x values. Now compute deviations from each observation subtracted. These will sometimes be positive if the observation is below x bar, or if the observation is below x bar, they'll be negative. If the observation is above x bar, these will be positive. You can easily show that if you add up the deviations from the mean, they add up to 0. The sum of squared deviations from this will measure how spread out x values are. If they're quite spread out, di's will be large. If they're more compact, di's will be small. The sample variance is sum of deviations from the mean squared divided by n minus 1. Originally, it was divided by n, but mathematicians found a better divisor than n minus 1. This is denoted by the symbol s squared. S is the square root of sample variance. Square root of sum xi minus x bar squared over n minus 1. The interpretations of S. In normal bell-shaped distributions, approximately 2/3 of the observations lie within one standard deviation. Approximately 95% lie within 2 standard deviations. If you draw a histogram of a normal distribution, it's a bell-shaped curve. Points of inflection are 1 standard deviation away from the points of inflection are where it changes from concave down to concave up. 2/3, as I mentioned before, 2/3 are within 1 standard deviation. 95% are within 2 standard deviations. Computing formula for the sample variance. The numerator is sum xi minus x bar squared. So to compute this, you'd have to subtract x bar from each xi and square it, and then do that sum. The difficulty is that when you subtract off x bar, it probably has a lot of decimal places. So xi minus x bar has a lot of decimal places. This will have this computation will involve a lot of decimal places. This is a better formula for calculating sum of deviations from the mean squared. You can show that that's equal to sum xi squared. So you're just squaring the raw observations, sum xi quantity squared divided by n. In tests, we'll give you those two sums there. So the sum of deviations from the mean squared, the easiest way is the right-hand side, sum xi squared minus sum xi quantity squared over. Divide by n minus 1, we get formula for s squared, the sample variance. Take the square root, we get the formula for the sample standard deviation. So you can do rough calculations of S. These are useful for checking your own calculation of S. S is approximately the range divided by 4. The reason for this, 95% of the observations lie between x bar minus 2s and x bar plus 2s. That means the maximum should be approximately x bar plus 2s. The minimum should be x bar minus 2s. If I subtract the 2, I'll get 4s. If I subtract the 2, I'll get the range. So S is approximately the range divided by 4. This is a good way to check your calculations for S. The pseudo-standard deviation. It's the interquartile range divided by 1.35. In normally distributed data, the pseudo-standard deviation and the standard deviation should be approximately the same value. For the normal distribution, the pseudo-standard deviation and the standard deviation will be approximately the same. If the distribution is leptokurtic, has a long tail, that means it can get extremely large values in both above the mean and below the mean. S will be larger than the pseudo-standard. For cladokurtic distributions, these are ones that have a short tail, a flat top. S will be smaller than pseudo-standard deviation. Measures of shape. These are the different aspects of shape. One is skewness. The other one we'll call kurtosis. In skewness, in the middle is the normal distribution. If the tail is elongated in one direction, either positive or negative, the distribution is skewed. So we want to measure that. Kurtosis measures is determined by the length of the heaviness of the tails. If the tails are short and are not long, compared to the normal distribution, say platykurtic distribution, if the tails are long, compared to the normal distribution and heavy, it's a leptokurtic distribution. These become very important in the mathematics of finance. Leptokurtic distributions, where these represent the distribution of change of a stock or an index. If that change is coming from a leptokurtic distribution, the changes could be wild. Coming from a platykurtic distribution, the changes are not so wild. To measure skewness, you use sum of deviations from the mean raised to the third power. Measure kurtosis, you use sum of deviations from the mean raised to the fourth power. The Fisher's measure of skewness is the average cube deviation from the mean divided by standard deviation. Fisher's measures of kurtosis, the average fourth, the average of deviations from the mean raised to the power 4 divided by S4. For a normal distribution, that first term should be about 3, so you subtract off 3 to make G2 equal to 0 for a normal distribution. These statistics are calculated by most packages. So you can, from those statistics, identify whether you were coming from a normal distribution or departures from a normal distribution could be a positively skewed distribution or a negatively skewed distribution, or one with positive kurtosis, one with negative kurtosis. Advanced box plots. These take into account extreme observation. The term outlier is an important term in statistics. It's an extreme observation. It could have occurred just because there was an error in writing down its value. In that case, it could be corrected. One checked it. It could occur because of extreme cases in the population. We'll now draw a box plot where outliers are identified. To do this, compute the median and the two quartiles, Q1 and Q3. Then we'll put fences around the population. The inner fences, you multiply the interquartile range by 1.5, subtract it from Q1 to get the lower inner fence, add it to Q3 to get the upper. To get the outer fences, we change the 1.5 to 3. Observations that are between the lower and upper inner fence are non-outliers. Observations that are between the inner fence and the outer fence, these are mild outliers. Observations that are outside the outer fences are extreme outliers. We plot these individually. Mild outliers will plot with a solid dot, extreme outliers with a circle. The non-outliers are then represented by the box whisker plot. The maximum in there are the largest observations within the fence, the smallest observation. Box plot should look something like that. Usually you don't draw the fences in the box plot. You just plot the outliers individually. And then the box and whisker plot is representing the major part of the data. Example, this is data collected on 109 countries in 1995. It was collected on 25 variables. These are some of the variables: population size, density, number of people per square kilometer. Another one is infant mortality, number 9, number of deaths of infants per 100 per 1,000. Here's the data in an SBS data file. There is a stem and leaf diagram of the data. From that, we can compute Q2, that's the middle one. There's 108 observations there, so it'd be average of the 54th and 55th observation. Q1 will be the median of the lower half, Q3 will be the median of the upper half. So from that, you can compute the interquartile range. You can compute the inner and outer fences. So all observations within the inner fences are non-outliers. Those between the inner fences and outer fences are mild outliers. Those that are outside the outer fences are extreme outliers. In this data, there's only one outlier. This is the infant mortality for Afghanistan. Another example. In this example, we're looking at weight gain under 6 different diets. So the test animals are rats. They're given, some are given one of, each rat is given one of the 6 diets. There's 10 animals on each diet. There's 3 high protein diets, and diets also differ in source of protein. There's the data for the 6 diets. 3 of them are high protein diets, 3 of them are low protein. The first step would be to compute summary statistics, measures of central location. They look to be agreeable. The mean and the median, probably because the data is normal. The interquartile range The pseudo-standard deviation is just the interquartile range divided by 1.35. The variance in the standard deviation, comparing the pseudo-standard deviation and the standard deviation, if they're approximately the same, that will be true if the data is normally distributed. There's a graph of the data. There was no outliers in this example. What you see is looks like the three low protein diets, the weight gain is smaller than the high protein meat diets before, but it doesn't look that much different from the high protein cereal diet. So from that graph, you can probably see that weight gain is higher for the high protein meat diets. Increasing the level of protein increases weight gain, but only if the source of protein is a meat source. The next topic we'll look at is multivariate. We'll look at descriptive techniques for multivariate. Most experiments, most studies collect data not just on a single variable, but on several variables. The graphical techniques. One is the scatter. This is probably the best one to use. You can also do two-dimensional histograms, but they're a little bit harder to construct. So you've got data collected on two variables, x and y. So they're done, a measurement of x and a measurement of y will be done for each case. Xi is the value of x for case I, yi value of y for case I as well. To construct a scatter plot, we plot the point xi for each case in the x. Here's some data. It's collected on 4 variables: verbal IQ, math IQ, initial reading achievement, final reading achievement. If I wanted to plot that, I'd need 4 dimensionals in order to plot. I can plot 2 variables at a time. Verbal IQ and math IQ. There's a scatter plot of verbal IQ and math IQ. Each point represents the 2 values on verbal IQ and math IQ. That's the point 84, 80. 84 for verbal IQ, 80 for math IQ. There's the same scatter plot, but I've stretched out the x-axis and the y-axis. Those are both the same graphs. Some patterns. This is one type of pattern in it. It's basically data that's contained within the circle. There's no relationship between x and y. You can't predict the value of x from the value of, or the value of y from the value of. You have a large value of x. There's quite a range of values for y. If you have a small value, it's a similar. So you're having a hard time predicting y. Here's another scattergram. This is in an ellipse, contained within an ellipse, and the ellipse is tilted upwards, which means that as you increase the value of x, the value of y generally increases. Not all the time, but for most part it is. So it's a positive relationship between x and y, increases in x corresponding increases in y. The major axis of the ellipse has a positive slope. Example, verbal IQ and math IQ. That looks like it's contained within an ellipse that has a positive slope. So if somebody has a high verbal IQ, he possibly has a high math IQ at the same time. Some more patterns. This is, again, contained within an ellipse, but the ellipse is much thinner. A stronger positive relationship between x and y. Increases in the value of x most of the time result in increases in the value of y. The major axis has a positive slope. The minor axis is much smaller. It's a thinner ellipse. Here's one where the minor axis of the ellipse is extremely small compared to the major axis. Increased strength in the positive relationship. Increases in x are almost always occurring when there's an increase in y. This is the other extreme. This time the ellipse is extremely thin. Its minor axis is 0. The data is falling perfectly along a straight line. It's a perfect positive relationship between y and x. The data falls exactly on a straight line, and if you know the equation of that line, you can predict y exactly in the value. Then you can get ones with a negative relationship. The axis is sloping down. So increases in x result in decreases in y. It's a negative relationship between x. Increases in x correspond to increases in y. The major axis of the ellipse has negative slope. The strength of the relationship can increase. The data become less scattered until the data lies perfectly along a straight line. Some nonlinear patterns. This is falling about not a straight line, but a parabola. The rate of increase in y is changing. It's going up at a much higher rate here. Then here it's actually flattened out, and before that it was negative. So in nonlinear patterns, the rate of increase in y depends on x. In linear patterns, the rate of increase is constant for no matter what the value of x is. A typical curve that is nonlinear is a growth pattern. In the beginning, the rate of growth is small, then it starts to increase, and then it starts to level out. Growth patterns frequently follow a sigmoid. Growth is slow at the start, then it speeds up, then it slows down as it's reaching its limit size. Review. scatter. Here's some scatter plot patterns. Circular, ellipsoid, with positive relationship between x and y. That means the ellipse is tilted upwards. Ellipsoidal, but with negative relationship. The ellipse is tilted down. Increases in x corresponds to decreases.
Excuse me.
Yes,
Excuse me. What is the major axis of the ellipse? What does that mean?
that's okay. Ellipse will have a elongated one. That's the, if you drew a line through the 2 points that were furthest apart, that's the major axis. Ellipse, the other axis is perpendicular to that. That's the minor axis.
Okay, thank you.
And so for this pattern up here, the minor axis is larger than the minor axis over here in relationship to the major axis. In a circle, okay, there's no major and minor axis. There's the nonlinear patterns that you can see. This one is parabolic. This one here is sigmoid. This is the usual pattern you see for growth. Where this one has been used is measuring the size of a tumor, a cancerous tumor. In the beginning, the tumor is very small, but as time goes on, it becomes larger. It may not become infinitely large, it might plateau out at a certain point. Measuring the strength of relationship, correlation. There's two statistics that measure that. Pearson's correlation coefficient, R, and Spearman's rank correlation coefficient, rho. So you've collected data on two variables, x and y. You can have the summary statistic that describe x, mean, variance, standard deviation, and so on. You can have also the summary statistics that describe y. Now we're going to look at statistics that measure the strength of the relationship between x and y. So the summary statistics for x is the mean for x. Summary statistic for y is the mean. And then you can have standard deviation, Sx and Sy. This is measuring variability in the x values. Sy is measuring variability in the y. So these give information about each variable separately. They give no information about the relationship between the two variables. Consider the following three statistics. This is takes xi minus x bar, squares that, sums that from I equals 1 to n. That's used to measure the variability in x's. If I divide that by n minus 1, I get the sample variances for the x's. Take the square root, I get the sample standard deviation. The next quantity is the sum of yi minus y bar squared. The last quantity is used for measuring the nature of the relationship between xi and yi. So the first two statistics are used to measure variability in each variable separately. If I divide them by n minus 1, take the square root, I get the sample standard deviations. The third statistic is to measure correlation. If the relationship is positively related, the sign of xi minus x bar and yi minus y bar will agree in some. If one is above X bar, the other one's above Y bar. One is below X bar, the other one is below Y bar. So when there's a positive relationship between Xi and Y, the two deviations from the mean will be positive. When when one is negative, the other one will likely be negative. The product will be positive. Here's some rules for multiplication. Plus times a plus equals a plus. A negative times a plus equals a negative. A plus times a negative equals a negative. A negative times a negative equals a plus. One way of remembering this, you do something good to somebody who's good, that's good. You do something bad to somebody who's good, that's bad. You do something good to somebody who's bad, that's bad. You do something bad to somebody who's bad, that's good. So in a positive relationship, the two terms usually agree in sign. They're both positive or both negative, sometimes not. Most of the terms in that sum will be positive. On the other hand, if the two variables are negatively related, the sign of yi minus y bar will be opposite in the sign of xi minus x. So in that case, the product will likely. So the statistic will be negative when there's a negative relationship, positive if there's a positive relationship. Pearson's correlation coefficient divides SXY, sum xi minus x bar, by the square root of sum xi minus x bar squared, sum yi minus y bar squared. The denominator is always going to be positive. The sign of R will be determined by the sign of SXY. If that sum is positive, there's a positive relationship between x and y. If it's negative, there's a negative relationship between x and y. This carries over to Pearson's R. It'll be positive. There's a positive relationship. Negative if there's a negative relationship. So the value of R you can show mathematically always has to be between -1 and +1. If the relationship is positive, R will be positive. If the relationship is negative, R will be negative. If there's no relationship, that means the positive products will balance out with the negative and it'll be 0. You can also show that if R is exactly equal to +1, the points xi, yi lie on a straight line with positive slope. If the value of R is -1, the points xi, yi lie perfectly along a straight line with negative slope. So these are some properties of R. Here, R would be +1. That's because it's lying perfectly along a straight line. If there's a bit of scatter, it won't be exactly +1, be a little bit less than +1. As the scatter increases, the value of R goes down. And when there's no relationship, R is equal to 0, then if there's a small negative relationship, it's minus a negative value. As the absolute value of R goes up to +1, the data gets closer and closer to a straight line. Some computing formulas for these three statistics. far right-hand side is the best way to compute xxx and syy. We looked at these ones when we were computing variance. The third one is similar to the first two, except it's working with products of xi's and y. So to compute those three quantities, first compute the following 5 sums, A, B, C, D, and E. Then A is going to be C minus SXX is going to be C minus A squared over N. SYY is going to be D minus B squared over N. SXY is E minus A times B over N. Example, verbal IQ. There's the data, math IQ. There's a scatter plot. From the scatter plot, you know that R is going to be positive, a little bit away from +1. So we compute these 5 sums. Sum of the x's, sum of the y's, sum of the x squareds, sum of the y squareds, sum of the products. SXX is just sum of the x squared minus sum of the x quantity squared over n. Same thing for y, work with the y values. And for the product one, we use the products. Sum xi yi minus product sum xi times sum yi over n. Then from there, we can compute r. It's sxy over square root sxx syy. Works out to be 0.769. You can sometimes guess that from the scatter plot. So this means that there's a positive relationship. If verbal IQ is above the mean, it's likely that math IQ will also be above the mean. If verbal IQ is below the mean, math IQ is also going to be below the mean. The final two measurements were final reading achievement and initial reading achievement. The improvement in reading achievement will be final minus initial. Is it more closely rated with verbal IQ or with math IQ? You'd think it'd be more closely related with verbal IQ. There's the data. This is the correlation of math IQ with reading achievement improvement. This is the correlation of verbal IQ with reading achievement. And you can see that it's higher, which you'd expect. Maybe at this point we'll stop and I'll answer questions. Again, I have to go. I have to end the meeting at 20 after.
Hey, I just had a quick question about the test marks. So once we submit the test, how will we be able to see what our marks are? Are they going to be uploaded onto Canvas or emailed, or what would happen there?
Actually, I'll be posting them on the website once the marks have been computed. So it'll be student number versus with marks. It'll be a table. So let me just stop sharing. Let me now share with the screen. I'll just make this smaller. So here is the here is the Stats 245 webpage. So after this one here, after the answer sheet, the marks will be posted after that, and that's where you'll find them. They'd be your student number with your mark. I think with Canvas, it's possible for once you've submitted the mark, the answers to get the mark right away. I'll try to see if I can do that.
I got a question about the assignment.
Okay,
I'm
sure.
kind of confused on the due date because on your webpage it says February 5th, I think, but on Canvas it says 22.
So it'll be the later of the two. Okay. So it'll be, so on my webpage, it says what?
I think it's like February 5th, but I can double check real quick.
Okay. Anyway, the due date will be the later of the two. So here it says January 22. So that will be the due date. I'll be showing you how to actually do that assignment in the lab.
Oh, okay, sorry. I was looking at the wrong one. I was looking at the assignments page with all the assignments, and
Okay.
that's for 2019, I guess. Okay.
Yeah. Yeah. If you go, these are just practice assignments for the different tests. I think this is incorrect. This was a previous year. So I'll make corrections on those.
One additional question before we run out of time here. You had your rough calculation of the standard deviation, which you said was range over 4. I'm assuming by looking at this that you're following the empirical rule. So my question is, if you can use over 4 because 95% of the data is within 2 standard deviations on either
Yeah.
side, why wouldn't we use over 6 because 99.7 are within 3 standard
Yeah.
deviations?
You could use that. It's a very good point. And dividing by 4 possibly gets you an approximation that's a little bit high. Over 6 probably gets you a better answer. But that's what most statisticians use is the over 4. This approximation is only good for normally distributed data. If the data is positively skewed or negatively skewed, this falls apart a bit. If the data is leptokurtic, platykurtic, it also falls apart as an approximation.
Hi, I got one question, another question. The midterm, like the test we just did, is there a way to tell that you submitted it properly afterwards?
Well, what happens is when you, if I go back, here's the answer sheet. if you go to the last question and submit the last question, if you fill out everything and submit the last question, it'll give you a notification that it's been submitted. The problem is if you're at the bottom of the page, you won't see that notification. You have to scroll up to the top of the page.
Okay, thank you.
Okay. So it should give you a notification that it's been submitted when you press the submit button. But you might not see it because you're at the bottom of the page and the notification is at the top of the page. Okay, so I'm going to end the meeting now. And I'll see some of you at the lab at 3:30.